Yes, good morning, everyone. So today we will discuss superposition theorem. Now this theorem is applicable on bilinear network when more than
Yes, good morning students. So today we will discuss superposition theorem. This theorem is applicable on the network having bilinear elements and more than one energy source. More than one energy source, right? That means whenever we are having multiple sources, I am talking about independent energy sources, right? Whenever we are having multiple energy sources, we will be active one source at a time, one source at a time, and deactivate the other sources. And this process will be repeated. This process will be repeated, and net current will be the vector sum of all the currents, right? Again I am repeating, this theorem is applicable on the bilinear network. This theorem is applicable on the bilinear network which are having more than one energy source. In this theorem, one network will be activated at the time and rest all are deactivated, and this process will be repeated for all the sources, and at the end we will be able to calculate that total current by taking vector sum of all the currents, right? I'm just taking this with one journal problem. So let us say this is your network. I'm taking this V1, R1, R2, R3, and here it will be again another voltage source of the value V2, right? I just want to apply superposition theorem on this network. So first of all, this network will be consist of resistive element. Resistive elements are bilinear element. Bilinear means current will be flowing in both the direction. Currents will be flowing in both the direction, either in clockwise or in anti-clockwise, right? Then after that, this network will consist of more than one energy source. More than one energy source. That means there are two voltage sources. There may be one voltage source and one current source, or two voltage source and one current source, right? So in this case, we will activate one voltage source at a time. One voltage source at a time, right? You may take step 1, activate one voltage source one voltage source. So let us consider I am taking it as V1 and deactivate all the other sources. Activate one voltage source. Let us suppose I am activating V1 and deactivate all the other energy sources. Right? So in this case, that basic steps regarding the voltage source and current source, that will remain same. Basic steps regarding the ideal voltage source and ideal current source, that will be same. So ideal voltage sources are having internal resistance as 0. Ideal voltage sources are having internal resistance as 0. So that's why we are just going to replace that voltage source with short circuit. Right? On the other hand, ideal current source are having infinite internal resistance. That's why we will replace it with open circuit. Again, I am repeating, ideal voltage sources are having 0 internal resistance. So that's why we will replace ideal voltage sources with short circuit, whereas ideal current sources are having infinite internal resistance. So that's why we will take ideal current sources as a open circuit condition while calculating the parameter of the network. Right? So in this particular case, we are assuming that there will be no current source. There is only two voltage sources. I am activating one voltage source. Let us suppose I am taking this. I want to calculate the current in each resistance. I want to calculate the current in each resistance by the use of superposition theorem. Right? Or it may be some particular load resistance will be given to you, R1, R2 or R3, that will be the load resistance, and we will have to apply superposition theorem to calculate the current in that particular resistance. But here, for your more understanding, I am just calculating the current in all the resistances. Right? So in very first step, I am just going to activate any one source. I am keeping V1 in the active state and V2 in the deactivate state. Deactivate means if the energy source is voltage source, then it will be replaced by short circuit, and if energy source is current source, then it will be replaced by open circuit, because voltage sources are having 0 internal resistance and current sources are having infinite internal resistance. So after applying first step, this will be your equivalent circuit. V1 will remain there because it is in the active state. R1, then here it will be R2, and it is R3. This voltage source will be replaced by short circuit. Right? Now this is the circuit after applying first step. So let us say this is your terminal A, B, C and D. Right? Now I want to calculate current in each branch. So first of all, you may apply KVL, KCL or simple Ohm's law to calculate current in the each branch. Important thing is here, we will also mention the direction of the current. In rest all theorem, either the case of the Thevenin theorem, either the case of the Norton theorem, or maximum power transfer theorem, in all that there is no particular direction. We are only interested in the magnitude of the current. But in case of the superposition theorem, we will have to apply the basics with its direction of the current, right? So here I am just applying the basic. So at across the voltage source terminal, across the voltage source terminal, across the voltage source terminal, equivalent resistance of the network, equivalent resistance of the network, that will be given by, let us take R equivalent is equal to, now here R2 is in parallel with R3 and this combination is in series with R1. R2 is in parallel with R3 and this combination is in series with R1, right? So this will be R2 R3 divided by R2 plus R3 plus R1. So this is your R equivalent across the voltage source terminal. Now let us say in this I1 is the I1 dash is the current, in this I2 dash and here I3 dash. This is the magnitude of the current I1 dash, I2 dash and I3 dash. Fine. With its direction, I1 dash is from A to B, I2 dash is from B to D and I3 dash is from B to C. Right. So here I1 dash, that may be calculated as this V1 upon R equivalent, right? And here direction will be from A to B, right? Then after that this I2 dash, that may be calculate, I2 dash that may be calculate by using current division method. Two resistances are in parallel, total current is I1 dash, I2 dash is equal to I1 dash into opposite resistance, that is R3 divided by sum of both the resistance, that is R2 plus R3, right? And here direction is from B to D, right? And last I3 dash, that may be calculated as again by using the current division method, that is total current I1 dash into opposite resistance. Now I want to calculate in R3, opposite is R2 divided by sum of both R2 plus R3 and here direction is from B to C, right? So these are three values of the current in three different resistances when only source V1 is present. When only source V1 is present, or we are saying that when only voltage source V1 is in the activated state and V2 is in the deactivated state, right? Now in the next step, I am considering the another energy source and deactivate the first. Step 2, activate voltage source, V2 and deactivate all the other energy sources. Right? I am writing here energy sources because if there are voltage sources, that will be replaced by short circuit, and if there are current sources, that will be replaced by open circuit. So here this is your V2. I am keeping it in activate state. So V2 is there, and R3, here it will be R2, and it is R1, and V1 is replaced by short circuit because V1 is a voltage source and voltage source will be replaced by short circuit, right? Because internal resistance of the voltage source, that will be 0, right? So here now R equivalent, let us say this is your R equivalent dash across the voltage source terminal, across voltage source terminals, that is V2, that is equal to, now see here R1 is in parallel with R2, R1 is in parallel with R2, and this combination is in series with R3. I am taking the terminals as same. This is your terminal A, B, C and D, right? So that direction will be compared. Now in this case, this is your energy source, so here current will be in this direction, I3 double dash, here it will be I2 double dash, and in this it will be I1 double dash, right? So here this will be R1 R2 R1 R2 divided by R1 plus R2 plus R3. This is your value of the R equivalent dash across the voltage source terminal V2, right? Now I3 double dash, I3 double dash, that will be due to voltage source V2, that is equal to V2 upon R equivalent dash, right? And I2 double dash and I1, this direction will be from C to B. Here direction will be from C to B because here V2 will be supplying the voltage. V2 is the energy source that will be used for supplying the voltage. So that's why direction of the current is from C to B, right? Then after that, I2 double dash and I1 double dash, that may be again calculated by using the current division method. So I2 double dash is equal to I3 double dash, I3 double dash into opposite resistance, that is R1 divided by R1 plus R2. Then this direction is from B to D. Then last I1 double dash, I1 double dash, that is equal to total current I3 double dash into opposite resistance, that is R2 divided by R1 plus R2. And here this direction will be from B to A. Direction will be from B to A, right? So I1 dash, I2 dash and I3 dash, that are the value of the current with its direction due to the voltage source V1, right? And I1 double dash, I2 double dash and I3 double dash, that are the value of the current with its direction due to voltage source V2, right? Now what to do? We want to calculate the total current by using superposition theorem. We want to calculate the total current by using superposition theorem. So here this total current is equal to, by using superposition theorem, by using superposition theorem, I1 total is equal to, now see here, I1 dash is in the direction of A to B and I1 double dash is the direction of B to A. So this will be I1 dash minus I1 double dash. I am assuming that I1 dash is greater than I1 double dash. In case of numerical, it will be clear. Whatsoever is greater, that will be subtracted from the second. If direction of the two current will be opposite to each other, then it will be subtraction of the current by keeping higher current in the first, right? So here I am assuming that I1 dash is having the greater magnitude. So direction of the current will be as per the direction of I1 dash. So I1 total is assumed to be having the direction as A to B, right? Then I2 total here, this will be in the direction B to D and this will be in the direction B to D. So both are in the same direction. Both are in the same direction. So this will be I2 dash plus I2 double dash and direction will be same. So that means this will be from B to D. Then I3 total, that will be equal to, here direction will be from B to C and here I3 dash and I3 double dash C to B opposite to each other. So this may be I3 dash double dash minus I3 dash, right? So I am keeping assuming that I3 double dash is larger, right? So that means direction will be as per the direction of I3 double dash. So that will be from C to B, right? So this is, these three equations are by the use of superposition theorem. By the use of superposition theorem. So see here, we will have to consider this direction of the current also. If direction of the current will be same, then it will be addition of the current, and if direction of the current will be different, then it will be subtraction of the current by keeping the higher value or larger magnitude current at the first. Because what I am saying, what does this mean? This means is I1 total, I2 total and I3 total that are always positive, that are required to be positive. So if, let us suppose this will be 2 ampere and this will be 3 ampere, then 3 minus 2, right? So direction of the current will be as per I1 double dash. So in case of numerical problem, we are keeping the higher magnitude current at the first and subtract it from the second, right? And if direction of the current will be same, if direction of the current will be same in both the cases or in all the cases, then it will be the addition of all the current, right? So by using superposition theorem, by keeping one energy source activate at one time and deactivate all the other energy sources, you will be able to calculate the current in any branch by the use of superposition theorem, right? So this is all about the this superposition theorem. Yes, now this is the network. one numerical based upon the Thevenin theorem. Calculate the power loss in 10 ohm resistance by using Thevenin theorem. Calculate the power loss in 10 ohm resistance by using this Thevenin theorem. So there may be two different methods, and result in both of the cases that will be same, right? So first step is I am just applying the steps whatsoever we had discussed in the that Thevenin theorem statement. Step 1 is, now this is your load resistance, because we want to calculate the current in 10 ohm resistance. So 10 ohm resistance is your load resistance. So step 1 is remove the load resistance. So here I am removing it. This is your terminal A, this is your terminal B. Fine. Now after step 1, this is your network. Remove the load resistance. Then after that, step 2 is this open circuit all the current sources and short circuit all the voltage sources. So here there will be two current sources, no voltage source, right? So this will be open circuit. After second step, this is your network. This current source will be open circuit. Here 2 ohm, 1, just check me the value of this second resistance. That will be 1 ohm, right? So this is of the value 1 ohm. So this will be 1 ohm, and here on the, this is your terminal A, this is your terminal B. This is again 1 ohm. This is your 2 ohm, and here this current source will be again open circuit, right? So see here, I want to calculate R equivalent here. R equivalent is the Thevenin equivalent resistance, that is RTH. I am keeping these terminal as A and B at the outside. Then at A, if you see, these two terminal will be connected together. These two terminal will be connected together. So 1 ohm and 2 ohm. 1 ohm and 2 ohm, this will be like this. Here it will be like this, right? So here this will be 1 ohm and 2 ohm, and then after that this will be connected with this 1 ohm resistance. This common terminal will be connected with 1 ohm resistance, and this is connected with B. And this resistance, because here it will be open circuit, so this will be nowhere while calculating the R equivalent. So this is your network. Here you will have to calculate R Thevenin. So R Thevenin is equal to 1 in parallel with 2. That means 1 into 2 upon 1 plus 2 plus 1, right? So this will be 2 by 3 plus 1, or this will be 5 by 3 ohm. So R Thevenin, I am writing it here, that will be 5 by 3 ohm. This is your first requirement. R Thevenin is equal to 5 by 3 ohm, and RL is equal to 10 ohm. That is given. RL is equal to 10 ohm. Now I want to calculate V Thevenin, right? Next is I want to calculate V Thevenin. For V Thevenin, this is your basic network, because after this again place all the energy sources in the network, right? Again place all the energy sources in the network, and after placing that energy sources, this is your network again. Now see here, if you see this current source is in parallel with the resistance. Current source is in parallel with resistance. So this may be converted into voltage source. Either you may apply KCL, but I want to change this current source because this is in parallel with resistance. So this may be converted into voltage source. So I into R, 2 ampere into 2 ohm, arrow is in the upward direction. So 4 volt voltage source, with it this 2 ohm resistance which is in parallel. Now this will be placed in series, right? And this will be the 1 ohm resistance, right? This is here one this side, and on the other side, because here this 2 ohm resistance is in series, so I am not able to convert it into voltage source form. So this will be remain as such. So this is your terminal A, this is your terminal B. Here it will be 1 ohm, 2 ohm, right? And here it will be 5 ampere. Now this is the network after converting current source into voltage source. After converting current source into voltage source, you may take as such, but I prefer to convert it because I feel easy after conversion this current source into voltage source, right? So after this, my aim is to calculate VTH here. VTH is VA minus VB or VB minus VA, whatsoever is higher, right? So here, this will be, this is a closed loop. This is a closed loop. In this closed loop, current I is flowing. So current I is equal to V by R, right? I is equal to V by R, 4 upon 2 plus 1. So that will be 4 by 3 ampere, right? 4 by 3 ampere. And here, because here this will be only one closed loop, so here current I is flowing. So VA, that is the voltage across this branch. So VA is equal to 4 by 3 into 1. So that will be 4 by 3 volt. 4 by 3 volt, right? So this will be, I think, 1.33 volt. 1.33 volt. VA is equal to 1.33 volt. Now see here, this is your node at the, because wherever we are having a voltage source, we will prefer to use KVL there, and wherever we are having current source, we will prefer to use KCL there. So at this node apply KCL, apply, let us suppose this is your node X, because here I am taking this as a B terminal, I am taking this as a node X. Apply nodal analysis, at node X, right? So at node X, apply nodal analysis means KCL. So algebraic sum of incoming current is equal to algebraic sum of outgoing current, right? So here it will be 5 ampere is incoming and same will be in the outgoing current direction. On this side it will be open circuit. So that means if current in 1 ohm resistance is I1, so that means I1 is equal to 5 ampere, right? I1 is equal to 5 ampere because this is your one branch, 2 ohm resistance and 5 ampere, that will be in series. So in 2 ohm resistance, 5 ampere total current will be flowing, and at this point this will be in the outward direction, right, in the downward direction. So in 1 ohm resistance, 5 ampere of the current will be flowing, right? And across this, our voltage is VB. So VB is equal to 5 into 1, I into R. I is 5 ampere and R is 1 ohm. So that will be 5 volt. VB is equal to 5 volt. VA is equal to 1.33 volt. So VTH is equal to 5 minus 1.33, or this will be like VB minus VA, VB minus VA, because VB is greater, right? So that will be 5 minus 1.33. So that will be 5 minus 1.33. That will be 3.67 volt. 5.00 1.33. Yes, it will be 3.67 volt. So your value of the VTH, that will be 3.67 volt. So I think all your this values will be equal to the values given in the numerical. Now make Thevenin equivalent network. Thevenin equivalent network, and Thevenin equivalent network will consist of VTH, RTH, and RL. VTH, RTH, and RL, right? So VTH will be 3.67 volt, RTH will be 5 by 3 ohm, and RL will be 10 ohm. So IL is equal to VTH divided by RTH plus RL. So this will be 3.67 divided by 10 plus 1.33. So this will be 3.67 divided by 11.33. So you may calculate it. That will be the required answer. That is the value of IL, and power loss across the 10 ohm resistance, that will be 3.67 divided by 11.33, its whole square into 10, right? So this will be, I'm just going to calculate it. Just wait. Just wait for a while. I'm calculating it. 3.67 divided by 11.33, that will be 0.33 approximately. So IL is equal to 0.33 ampere, right? 3239. I'm taking it as a 0.33 ampere. Now 0.33, it's a square. 0.33 into 0.33, 0.33 into 0.33 multiplied by 10. So this will be approximately 1 watt. Power consumed is 1 watt. So 1 watt is the required answer. By the use of 1 watt is the required answer. Current is 0.33 ampere and power is 1 watt by the use of this Thevenin theorem. So this is the end of the lecture. We will meet in next lecture again. Right? Thank you.
Thank you, sir.
Thank you, sir.